A machine is defined as any device that makes work easier. Can you identify this sound? Yes, this is a leg pounder. It makes work easier, so it is a machine. But this is not similar to the bigger machines that you saw at the beginning. This is just a simple machine because it has only one moving part. Why are simple machines called simple? Because most have only one moving part. When you put two or more simple machines together, you get a complex machine. Lever, pulley, inclined plane, wedge, wheel and axle, screw are all types of simple machines. Look at this seesaw. Do you know it or not? It is also a simple machine. How is this a simple machine? Think about it, how easily you can move up and down in a seesaw. If there was no seesaw and you still wanted to move up and down, what would you do? Maybe you would have to ask for a strong friend to carry you up and down. Think how difficult would that be? Seesaw is a machine because it makes playing easier. And yes, playing is also a work. Are you surprised? When anybody moves or gets moved, we call it a work in a science. Seesaw is a simple machine because it has only one moving part and it does not have any other additional machine. Now, let's see how does it work. Here, when a downward force is applied on one side, upward force is applied on the other side. At the moment, downward force is applied by the person on the right side, which is called input force or effort. Because of the input force, another force is acting upwards that is helping to lift the person on the left. We call it output force, which is same as the load. The point on the middle that is fixed is called fulcrum. This machine, which rotates about the fulcrum, is called lever. It is a simple machine, perhaps the simplest one. You just noticed that there was effort on the right side, load on the left, and fulcrum at the middle. Now, when the person on the left is moving downwards, she is applying downward force. That makes the person on the right side to lift. Therefore, effort is on the left and load is on the right this time. But fulcrum is still at the middle. Such type of lever in which fulcrum is in between load and effort is called first-class lever. Can you give another example of first-class lever? Another common example is a pair of scissors. When you cut a paper using scissors, your finger will be applying effort at one end. Due to the effort, the sharp edges on the other end will exert force on the paper. This part is therefore the load, and the fixed point at the middle is fulcrum. Actually, there are two levers in a pair of scissors and two wedges sharp parts, so a pair of scissors can be called a compound machine. But the levers in the scissors are simple machines that are first-class levers because fulcrum lies between load and effort in them. At any given time, a lever has 3 points: effort point, load point, and fulcrum point. The distance from fulcrum point to effort point is called effort distance. Likewise, the distance from the fulcrum point to the load point is called load distance. Similarly, the arm of the lever towards effort from the fulcrum is called effort arm, and the arm towards load from the fulcrum point is called load arm. Now, look at another example. Here you can see a wheelbarrow. There is a lever in it. Can you identify the effort, load, and the fulcrum points? Yes, here load is in the middle, effort is on the right, and fulcrum on the left. The hands are applying upward forces on the right side of the lever. The stones on the middle act as load, and the center of the wheel on the left is the fulcrum. Such lever, which has load between effort and fulcrum, is called second-class lever. Another example of second-class lever is bottle opener. As you can see in the picture, it also has got load between fulcrum and effort. What is in the middle in a third-class lever? Can you guess? Yes, a third-class lever has effort in the middle. Now, think of an example. You don't have to go far. Your arm is a third-class lever. You don't believe? Look at this. When you raise some load with your hand, your arm muscles will pull at the lower arm. That is effort. Here, fulcrum is your elbow about which your lower arm moves. Forceps are another fairly common example of third-class lever. Effort is applied at the middle in forceps. Now we know that there are 3 classes of levers. First-class levers have fulcrum in the middle. A pair of scissors is an example. Second-class levers have load in the middle. Wheelbarrow is one such lever. A lever that has effort in the middle is third-class lever, forceps being one example. How does a simple machine make work easier? Let's see it. Using first-class lever, we can move a load in opposite direction by applying effort at the desired direction. Take a look at this picture. If you had to apply force upward in a seesaw, imagine how difficult it will be. When we apply force upward this way, we are working against the force of gravity. That's why it's difficult. But when we apply force downward, the same force of gravity is helping, since force of gravity is always applied downward. In this way, we can apply downward effort to lift a load. Do you remember the effort arm and load arm that we had mentioned earlier in the lever? We had also talked about effort distance and load distance. Let's see what happens when effort distance and load distance are changed in a first-class lever. When load distance is decreased and effort distance is increased, more weight can be lifted using less effort. Likewise, when effort distance is decreased and load distance is increased, more effort is required, but the load can be lifted much higher and faster. Just like lever, other simple machines make our work easier in the same way. To lift more weight using less effort, to increase the speed of work, to change the direction of effort. In science, work is said to be done when a body is moved from one position to another. When working with the help of a machine, work is being done in 2 places. One place is when effort or input force is being applied, and another is when load or output force is being applied. We can call it input work and output work. In this picture, there is a machine where someone is applying effort or input force on the left side, which is causing output force on the load on the right. Here, consider the distance crossed by effort force as x. Similarly, consider the distance crossed by load or output force as y. You know that work is equal to force multiplied by distance. That's why here input work equals input force E and x multiplication. Similarly, output work equals output force L and y's multiplication. Input work is the work done by applying effort in a machine, and output work is the work done by a machine upon the load. In this machine, if there is no any type of power loss, then such machines are called ideal machine. Its principle indicates input work equals output work. So, according to the same principle, in a lever, multiplication of load and load distance equals multiplication of effort and effort distance. Hence, you saw it in the example of seesaw how even a less weighted person can increase their effort distance to lift a more weighted person. This principle is applied in all types of lever, meaning in every condition, load into load distance equals effort into effort distance. Let's see what these kids are doing. They are using a spoon to uplift a ball. Now, can you tell me if this is a simple machine?
Yes, it is.
Which simple machine is this?
Lever.
Can you answer what type of lever is this? The effort in the tail of the spoon is load. When you press the tail of the spoon, you are applying effort, and fulcrum is in the middle. What type of lever has fulcrum in the middle?
First class lever. First class lever.
Yes, good work. This is a first class lever. Now, I will show you examples of levers one by one. Identify which type of lever it is. Beam balance. Stapler. This part of nail cutter. The other part of nail cutter. Fishing rod. Breaking a walnut. Leg pounder. Well done, kids. Now everything must have been clear to you, right? Are simple machines you see around lever? If yes, what type of lever are they? Has it more than one type of lever in use? Look closely.